Event biasing. And these slides were developed by our colleague Marc Verderi at École Polytechnique. He is something of an artist himself. He did this painting, and the painting, as you can see, is biased, so it's an appropriate picture. I will discuss some general ideas about biasing, and then talk about the biasing options that we had in Geant4 before 10.0. We still have them, so I will talk about those. And then I'll finish up with a new, very general approach, which we're still learning how to use, but it is very comprehensive, and it could do a lot of things for biasing applications. So what is it? What is event biasing? It is, formally speaking, variance reduction. So we are trying to increase our statistics and accelerate the simulation in an area of interest to us. So suppose it's a rare decay or some kind of rare event, and we want to accelerate the rare part, but we don't want to accelerate everything else. So we're biasing our attention. We're paying attention more to the rare stuff and letting the other stuff go. So if we do this, we focus on what we're really wanting to tally or to score. And depending on the application, this could have really large improvements in CPU time, several orders of magnitude in many cases. But it's technical. You have to understand what you're doing. Otherwise, you can make big mistakes. So it's important to understand all the biasing methods. Biasing stands for using a biased simulation. And once you do something like bias the cross-section or bias the region in which you're operating, you also have to remember that whenever you do that, that comes along with changing the weight of the particle. So if you increase the cross-section by a factor of 10, then you have to decrease the weight of the particle by a factor of 10, and so on and so forth. So that's the other side of the story. And then when you combine everything back together, the particles that were biased have a higher weight, and the particles that were not biased have a lower weight. So when you sum that all up, it comes out to the correct answer. There are many, many biasing techniques, but if you look at them, they usually can be resolved into two separate things. There is importance sampling and splitting. And so usually it's just a combination of these things that do lots of different biasing applications. So let's look at importance sampling first. This simply changes the probability distribution function. So the PDFs are replaced. This might be, this curve here might be the natural physical spectrum that you get from some reaction. But you are interested only in this, let's say, high energy region, which is, not happening very often. And so what you really want to do is change this PDF to this PDF, because now that concentrates on the region of physics that you're interested in. And so when you do that, you now have to figure out what the weight is going to be for any particles generated using this spectrum. And so that is just this weight function. The unbiased or analog PDF divided by the biased PDF. So you just divide this function by that function, and you get the weight. And then you apply that to any particles that are generated under these conditions. Some examples. One is very popular, the exponential transform technique. So this is where you actually change the cross-section. On the first day when we talked about statistical and simulation methods, we talked about an exponential decay profile. So we have some decay time or some cross-section, which could give you a mean free path or something like that. And you have a PDF which looks like this. If you change the cross-section, or for example, if you're moving forward or moving backward, you change the behavior of that function. So the analog law or the unbiased law looks like this, and the biased law could look like that. Another thing you can do is force the interaction to happen in a thin volume. So let's say you have a small scintillator plane or maybe a thin gas volume in which you want to detect some particles. But the interaction cross-section is obviously, or the total cross-section or probability of a particle interacting in that region is going to be small because it's thin or it has low density or something like that. And so the unbiased function might look something like this. So this is, a small cross-section for an exponential decay or something like that. But you want it to happen in this thin volume. So this x-axis represents the thickness or the distance of the particle. And here is the volume boundary. And so you say, I only want to look at whatever happens in this distance. And so you can force it to happen. And there's a way to do the biasing which will allow you to do that correctly. That was importance sampling. And now we look at splitting. So a good application of this would be to find out how many particles come out on the far side of a big block of lead. So you're sending in a beam of protons. How many reach the far side? Obviously, lead is used for shielding, and so you're going to have very many coming in and very, very few coming out. And you're more interested in what's coming out, and so you have to do something in order to save yourself a lot of computation time. And so what you can do here is set up an importance, geometrical importance region. And then as the particles traverse each importance region, you split them. So in this particular example, you could say that this region has weight 1, this region has weight 2, 4, 8, 16, and so on and so forth. You can change this. It doesn't have to be a factor of 2. It could be a factor of 3 or whatever. But 2 is usually what people like to use. And so as a particle is coming from the beam, and it goes from a region where the weight is, let's say, 4 into a region where it's 8, then what the biasing will do is make a clone of this particle. So it'll make an identical copy in the same direction and the same energy and all of that. So where there was 1, it crosses the boundary, now there are 2. Okay, that's a bias, so what do you have to do? You have to reduce the weight of these 2 particles by a factor of 2. And then if you go to the next region, you do the same. You have 4 particles, and the weight is reduced again. So by the time you get to the end, you have a few particles that survive, but they have a very high weight. Now, let's suppose that there's some scattering, and these particles, after they're created, wind up going in a backward direction. So now they're going from a high significance region to a low significant region, and you say, well, now I got 2 of these going in here, but because I weighted it by a factor of 2 going this way, I have to somehow decrease what's happening in the opposite direction. So here, we have to decide to kill one of the particles. So if it's a factor of 2, we roll the dice, and we say, one of these has to be stopped and removed, and the other one gets to continue. We call this killing or Russian roulette. So that's splitting. Now I'll go through some of the biasing options that we've had in Geant4 for a long time and still have. And by the way, there is an extended example set called biasing, in which it runs through all of these options. So you can find a lot of information, and the READMEs are included, so there is documentation. Primary particle biasing. So Makoto mentioned the general particle source. So that allows a particle to be biased. As he said, there are a lot of commands, probably more than anybody knows. And you can bias things like the position, the angular distribution. That's an easy one. So instead of into 4 pi, you emit particles into a narrow cone, and the biasing is applied appropriately. Energy distribution can be biased, so that's an importance biasing. So all of these, as I mentioned, are importance biasing. So physical distributions here are replaced by the biased ones. So we're changing the PDF. And the particles have to be given a weight. So we divide the physical law by the bias law, and we get the weight. There are some rather old biasing options in the hadronic code. Many of them are not used, but they're still there. So if you, for example, have a small cross-section, and a good example of this is electronuclear. So the cross-section is quite small compared to hadronic interactions. But that's what you're really interested in. So if you want to look at photon inelastic or electron-positron nuclear processes and bias those with respect to the hadronic processes or other electromagnetic processes, what you can do is do a biasing. So here we're doing what we did when we talked about processes. We create the model, and we assign the model to the process. And now we have a pointer to the process, we just do this bias cross-section by factor, 100. So we're multiplying the cross-section. This is the easiest kind of biasing. And that means that reaction is going to happen a lot faster. And then we register the process to the particle manager, and we're done. So that's all you have to do for this kind of biasing. Leading particle biasing. So if you're interested in looking at hadronic showers or hadronic interactions tend to produce a lot of secondaries. And then those secondaries produce a lot more secondaries. And so it is sometimes useful if you want to speed things up to do something called leading particle biasing. So in a case where you have maybe 9 secondaries, what you do is select only the highest energy particle and one representative of each other particle type. So it could be the leading particle and then one pion or one kaon or something like that. So it reduces the number, but it still gives you a representative or a representation of the kind of event that you had. Very approximate. I don't know of anybody who uses it anymore, but it's still available. As I mentioned yesterday, the radioactive decay package has a lot of biasing options, and these are very similar to what we've already talked about. So we can enhance a particular decay within a given time window. We can sample all the decay modes with an equal probability, and we can split. So we can do splitting here. If we have a nucleus that rarely decays, we can say, oh, well, go ahead and do it 100 times. So we can set that factor, and then we can enhance the emission in a particular direction. The importance biasing I already mentioned, but this gives you a little more idea of what's going on. You can set these importance cells. As I mentioned, this is importance factor 4 and then 8, and it just increases as you go toward the tallying point. And, okay, I guess there's nothing new here. I pretty much covered all of that, so let's skip to the next. Here's an example of an event in which this importance biasing is used. So if you just did the straight Geant4 simulation of some particles going through some thick shielding, this is what you would get. Particles go in, they're either absorbed or they scatter, and the secondaries are absorbed almost immediately. And you would have to run for a very long time before the probability of getting something coming out the other end would be possible. Now, if you use the importance sampling, and this is now a factor of 2 for every layer, then this allows a lot of detail. And so at the end, you have some particles actually getting through after only a few events, but their weight is very high. It's 2 to the n, however many layers you have here. There is a more sophisticated way to do this. So if we go back here and we look at the particles coming out, these particles would have a very high weight, and there would be very few of them. So when you do the final tally, you may find that you have a very few particles getting through, even so, but they have high weights. And the fact that you have a few particles with high weights means that you're going to have perhaps difficulty in converging to a mean. Okay, you could have a weight which is 0.1 and then a weight which is 1,000, and you can see with a lot of differences like that, the convergence to a mean, which is what you want, becomes difficult. Also, if you have particles going backwards, so they can lose significance, and you can have particles with very small weights. And if the particle has a small weight, why bother tracking it? It just costs time. So what you can do is something called a weight window. You can say if the weight gets too low, use the Russian roulette to kill it. So some fraction of the time you just remove this particle. It's no longer important. It has a small weight and it won't affect your tally. If the weight gets too large to the point where you're worried about convergence of the mean in the final result, then you can do more splitting. So this is a method that allows you to have more control and come to a better convergence when you're doing biasing in the importance method. Questions so far? Okay, here's a neat one. Reverse Monte Carlo. So this is a case where we have Geant4 particles going backwards in time. We actually have processes which do that. So we might apply it to the following situation. We might have some small device which is seeing radiation from a large background spread out perhaps over the whole sky if it's a chip inside of a satellite. It could also be some gem detector inside of a large detector, and you know that you have background coming from everywhere in the detector, but you only want to look at what is near your small component. And so this was developed, requested by ESA and developed by one of our collaborators. And the way it works is to start a simulation in a small volume. So here is the center of this small volume, and this is your component, let's say. And you're really interested in what's happening in this region inside the dotted circle. So how do you avoid the fact that when you have a source which is out here, and you're sending particles in from that extended source, most of them are going to miss this, and you'll spend a lot of time before you even get one particle coming into the area of interest. So what you can do is draw some kind of circle or sphere around your area of interest, and then you release a track going outward, and we call this an adjoint track. It's going backwards in time, so we call that adjoint. So it goes back in time, so the time is decreasing. It's going out through material, so it's increasing in energy. And if there's a secondary, some of the secondaries can come back in and be merged into the track. So Bremsstrahlung, for example, has been written as an adjoint process, so you can do the process backwards. Now, this particle goes backward in time, but outward in space until it reaches the point of your source, or the surface of your source. And then you just keep doing this for a fairly large number of tracks. But this is how you start the first track. Okay? So the track is released, it goes to the source, and then you check, is that less than the highest energy limit of the source spectrum? You don't want it to be too high, otherwise that means you're doing an incorrect biasing of the source. If so, then you make a second part of the track. So this is the backward in time part. Now you do the forward in time part, which is the green. So from this same point that you started the original track, you send the regular Geant4 process, which goes in forward time. And now you have a complete track as if you had started it somewhere here, or rather as if you had started it here, and it goes now forward in time all the way to some point where it is absorbed or interacts or something like that. So now you have one complete track which has sampled all the material and has come from the source, but because you started here and went backwards in time, it's a biased distribution by the time you get to the sky source. So what you need to do is do a weight calculation on the surface of the source. You know the spectrum for the adjoint track, and you know the spectrum for the sky source. Just take the ratio of the two, and that gives you the weight for each of these combined tracks. And that's how you do that. Questions about that? I know it's a little confusing, but do you get the basic idea? Okay? Great. Very useful. used a lot of applications. Now we go on to a much more general type of biasing, and this was developed by our colleague Mark. And we wanted to try and make things a little easier by making them more general. That's sometimes a little difficult, but we realized that using some of the methods and processes in Geant4 for biasing are a little difficult, and some things are not necessarily easy. So with user-defined biasing, we have something called a G4 wrapper process. And that basically means that we take a conventional process like Bremsstrahlung and put it inside or wrap it inside another process. And so this is a process like any other, but it just gives you a hook into the control of the usual Geant4 process, so you can bias it. You have calls to this wrapper function. It simply forwards the call to the wrapped process. So what you need to do is create a derived class inheriting from G4 wrapper process, and then you need to override the specific method. So the one that you're going to need to do is post-step do it, and then register this class instead of the original process. So there would be wrapped Bremsstrahlung, use that instead of the Bremsstrahlung process. And then register this to the particle. So here's how you might do that. Here's an example for Bremsstrahlung splitting. This is used a lot in medical applications. The cross-section for the emission of a Bremsstrahlung gamma is rather small. And so what they wind up doing is say, whenever you have one Bremsstrahlung happen, emit 1,000 gammas. And then you need to run many, many fewer events with the incident electron or charged particle. So it's used a lot for radiotherapy and photon beams. The process can be repeated n times, so you get to choose how many gammas are emitted per Bremsstrahlung interaction. And then once you do this, the weight of the photons are given as 1 over n. So that is correctly done. So let's go through it. So here's this process which you have developed. We'll call it my wrapped process. And as I mentioned on the two previous slides, you have to override the post-step do it. So you have to tell it what's going to happen at the interaction point. First thing you do is set up the weight, so the track weight you can get. And then this is your splitting factor, let's say 1,000. And then set up your secondaries, because you're going to create 1,000 secondaries in this case. And then go ahead and repeat this loop 1,000 times. And in this loop, you take the regular process, so this is the unmodified or analog Bremsstrahlung process that we use all the time, and say, use its post-step do it. Now that we've done that, that produces secondaries. The secondaries get put on the stack, and now they're ready for further propagation. And then this just repeats for each time that you want to split the gamma that comes from Bremsstrahlung. So here's what it looks like when we run it in an example. Here's a scoring sphere, and here is some particle accelerator emitting electrons. And it's going through some foil here. And the normal case without splitting is that for each electron which is emitted, you get one Bremsstrahlung photon, and it is scored here. Now here with a splitting factor of 100, you get 100 such gammas. So now you can see that with one electron, you already get a good sampling of the Bremsstrahlung on your scoring sphere. So there are many options, but they really aren't easy to change the probability distributions, at least what has gone before 10.0. Since 10.0, we have some ways to improve that. So it's not particularly easy to change the final state behavior. It has not been easy to change the biasing mixing. So if we want to include importance biasing with importance regions and things like that, it wasn't particularly easy in the past. So the current general scheme hopes to improve that. So we will be able to do things like exponential transform, as I mentioned. So we can change the total cross-section, make the change direction dependent. We can do things like forced interaction. So here's a thin volume, and we want to make sure that it always interacts in that volume. And we can do forced flight. So forced flight is an interesting thing which you have to do, and we don't deal with it very much in Geant4, but the proper thing to do is always do forced flight, and I'll tell you what that's about in a minute. So all of this can be combined. You can take all of these pieces and combine them into a very complicated biasing operation so that the weights will be applied in a consistent way. That's the goal of this. So let's talk about the forced collision again. And this is the proper way to do it. So you've got a thin target, and you can say, I want the cross-section to be bigger, or I want to make sure that the cross-section or that the interaction happens in this thin target. So what do? The proper way to do it is take the incoming particle, and when it reaches the boundary of the target, split it into two. One of those tracks then is forced to interact. So we call this the forced collision part right here. And we know what the weight is going to be for that. It's 1 minus e to the minus cross-section times the traveled length. And so we can sample that distance. And if we do the forced collision formula to do the biasing, we know that it has to happen within this range. So you can't stop there, though. Even though you've done the interaction and you've applied a weight to it, what you have so far ignored is the possibility that the particle could go completely through and not interact. So that's why the splitting. We split it so that one particle can interact. The other particle is forced to go all the way through. And the weight for the particle that goes all the way through is just basically this e to the minus sigma L. So we just divide it up so that the sum of the weights is going to be W0. But the particle going through has this weight, the particle interacting has this weight, and now we have a situation where the weighting is correct. This is an idea that you can split these so that in our general approach, you can do something different for this piece and something different for this piece and still have the weighting done in a consistent way. So each of these pieces is a different biasing technique, and we can combine them to do the right thing. Now, this is kind of how the whole thing works. So I'm going to go through step by step what happens when you do this complicated biasing. And this is just an example. So let's talk about first the point-like processes, so photoelectric effect, gamma conversion, and Compton scattering. And this is an example we talked about a while. Photoelectric effect has a small cross-section, so its mean free path is longer. Gamma conversion has a larger cross-section, so its mean free path is shorter, and then Compton scattering is somewhere in between. So the usual thing in Geant4 is that get post-step physical interaction length returns the distance for each of these processes by sampling the mean free path. And then you have a long one, a short one, a medium one. Geant4 always takes the shortest one, does the interaction, and produces secondaries. Now we go to the biased operation. So suppose we have a biased operation, then that means that this analog behavior that we talked about before need not happen. So let's suppose that we're more interested in gamma conversion, and so we can have our biasing operator say, let's do gamma conversion more often. The others are still on, but gamma conversion will happen more often. And so now we have the situation where we have biased it so that there's Compton scattering, and we produce that event instead of the ordinary one, which would have been gamma conversion. So that's the first part of the biasing. And now here is kind of a physical picture of how the biasing would go. Let's say you have some geometry here, and this volume there's no biasing in this volume. There is biasing in this volume, and there's no biasing in this volume. And here we have something called my biasing operator. So this is like the big boss. This is the class that does everything, but you have to write most of it. So this is the boss that looks at all of these resources, combines them together, and applies them to all of the processes that you've assigned via the wrapper class. So this is the boss class. It says, I want these resources, and I want them assigned to these processes, only when we're in this volume. So my biasing operator is attached to a volume. So when we do this, it's as I mentioned before, in the wrapper class, we have this biasing processor interface which looks at the wrapper and says, I have a wrapper class around photoelectric effect, so I'm going to bias photoelectric effect, or I'm going to bias gamma conversion, or I'm going to bias Compton scattering. So that happens when the particle enters the volume, and then the particle propagates under these processes. And now the particle comes to the volume boundary. And so now these processes have to talk to the biasing operators, because I'm in this volume, the boss class takes over. It says all of these are active now. Now the biasing operator in this case, in this example, says, I want splitting. It could have been some other thing. It could have been cross-section biasing. But in this particular example, it says, I want to split the particle. So it says, take the splitting operation, which we talked about before, and apply it to the processing interface. Okay, right now it doesn't have a process, but it just knows that it's going to do splitting. And now, once the biasing operator is consulted, it says which process is going to be split. Could be all of them, it could be one of them, or something like that. Now the biasing operator says, we're going to do a forced interaction for one of these tracks. So we've already split them, but one of these tracks we're going to force to interact in this volume. So we use forced interaction with the exponential law. And then that is applied to these processes. And then that goes on through the unbiased volume and so on and so forth. Now we deal with the other track, and that is going to, once again, invoke all of these processes. But now the biasing operator says, I have to do the other part of the operation. Because I forced the interaction in the first place, I now have to balance that off with the forced free flight. So I have to send it through without interaction. So that's the next step that the biasing operator does. Okay, so that's the kind of an example of how that goes. How you might do that in your main program. So this is where you invoke it. So you will have some kind of physics list. And then here's where you do the biasing. So you have G4 generic biasing physics, and you're going to get a pointer to that. And now you're going to say, I want to bias the gamma, I want to bias the neutron, and I'll register this to the physics list. So now I know that these particles are going to be biased. And then do the set initialization just like you would when you're building your own main. Now, as you recall, there was this biasing operator that was attached to a volume. So in your construct detector part of the main, you have to do this. You have to take your biasing operator, which you have written, and instantiate it and attach it to the particular volume that you're interested in. So the logical volume is the argument here. So here are the examples. Here's where you want to go. Examples, extended, biasing GB01. So this is individual process cross-section biasing. And then GB02. This does the same kind of biasing which is done in MCMP. So we kind of noticed that MCMP has been doing biasing for a lot longer than Geant4 has. So they have a lot of expertise at it, and we're trying to catch up. So we can allow this the same kind of behavior so that you can do some comparisons. And some more examples are under development, but these are two good places to get started. So this is biasing operations or operators. You can define a whole bunch of functionalities by using the virtual class. So G4 virtual biasing operation and G4V biasing operator. With those, you can really extend a lot of the biasing capabilities. So, as I mentioned earlier, and Mark notes here, this development is fairly young. Okay, we're still learning about it. And maybe you will become the new experts because you're learning about it along with us. That's it for biasing. We have lots of biasing techniques. And so if you're careful, you can have very large speed increases in problems by using biasing. And we have several things: primary source biasing, cross-section biasing, radioactive decay, importance biasing in geometry, weight windows, splitting. The new toolkit-like approach that we have since version 10 allows you to mix all of these in some consistent way. So we have a big general master plan for doing that, and that's quite nice, something you should try. So these things are often a little delicate. You have to make sure that you really understand what you're doing. Biasing is dangerous, okay? So when you do it, validate, validate, validate. Only then can you trust that you've done the correct thing. That's it. Questions? Yes.
I have a question with slide 18.
Okay.
So I imagine that we have to be careful when we choose this split factor, right?
Yes.
What happens if I choose a very high number?
Well, one of the things that might perhaps lead you to a mistake is if you have a very high number of splittings, let's say 1 million gammas, and then you look at your final state histogram and say, oh, I've got a full spectrum because I've got millions of gammas. And then you realize, oh, but I only threw 2 original electrons. So then you're not sampling the original particle perhaps enough. So it's not really an error, but it could lead you to the wrong result by not doing enough of the original particle throwing. That's one particular thing. Oops. The other thing is, if it happens to be a cross-section biasing, and you are looking at a case where, let's say, in a hadronic situation where there are multiple hadron scatterings, the hadronic cross-section is already rather large. If you bias it to be a factor of 10 larger, then you will really significantly distort the final result of the scattering. In a sense, because a lot of these things are done with perturbation calculations, and we assume that the cross-section is relatively small. But if it's large, those approximations don't work anymore. And this is especially true for electromagnetic, where you have the 1 over 137 factor that you would depend on to be small. If you make that too big, then you're going to find some electromagnetic reactions are not going to look right. So that kind of a thing you have to worry about as well. There was a question? Yeah?
So we have this region. How do we implement? Do we use region? How do we implement that? In this area, we're going to have dieting, and the other one is without dieting.
Right. And it's based on region. Yes. So G4 region.
This region.
Yeah.
Region bias.
Yep.
Then
Yep.
all the bias region in your detector will follow.
No, only you can assign one region to be biased. It doesn't have to be all the regions.
No. Yeah.
Yeah.
I mean, let's say that I have several pieces of my detector. Then
Yes.
Then the biasing will happen in all this.
Everything in that region. Yes.
Or you can put mother body that big, like one meter, one logical mother body. Anyway, we know we associate the logical.
Other questions? Yes. Yes. Mm-hmm. We're recording in a small volume. Usually it's a case where the source is very extended. And we're recording in a small area. Yes, that's the application for that.
In that small area, I had complicated cells, for example. I had to create using the parallel world. I still using a parallel world.
It doesn't have to be parallel world. You can, but it's not required for the reverse Monte Carlo. Okay.
Hey, morning. Yes, it already has come to the last day. So this is second multi-threading talk. It has three components. The first one is kind of important. It has only one quite important information. When you write your own class, use a stepping action or a sensitive detector or whatever, you really have to consider just one thing, thread safety. Okay? The second one is just blah blah. And if you really need to employ hundreds or thousands of nodes, each of them has many threads, you may want to come back and see just a few slides. Okay? And we do have some examples, so I don't think we have to go too much detail about it. Then the last one is quite important. Even your application runs on your laptop only. As long as if you have more than one thread running in parallel, this is important. Okay, let's go. The first is thread safety. So here's some blah blah, but anyway, the key thing is, suppose this is a function, okay? And this is very simple, stupid function. If this variable is positive, do something, and set this flag to the negative. And next time you come back to this function, if it is this one is negative, do something else, and reverse it back to the one. So it's you just do this one, that one, this one, that one, repeating. Okay, basically simple algorithm. So if you have only one object or memory space of this variable in the memory, and if you have two threads running in parallel, you cannot expect each thread to do the correct thing, because once thread A comes to this point, it could be positive, so it do something. But before finishing do something, and so that it's set to the negative, second thread come here. Okay? Then this one is still positive, so this one also do something. Okay? And so as you can imagine, you cannot predict which thread comes first, and you cannot predict you can finish this line before the other one comes to this if statement. We call this a race condition. It's really a unpredictable, issue. So you really have to avoid this when you write user stepping action or something like that. If you have a data member that is shared, it's a nightmare. And of course, you say you'll never do these stupid things. But often, for some reason, people put keyword static, okay, data member, or even a method local variable. You put static because you want to remember the values for next time. It often happens. And if you run it in multi-threaded mode, bingo. Okay? If you put static keyword, that is shared by all the threads. Okay? So be careful. Okay? And so I have already explained this is the issue. Okay? So to avoid this, there are two ways. There are two ways to avoid this. The first one is so-called mutex lock mechanism. This is something that when you write mutex lock and unlock, then when program comes to this point, this part is blocked. So if other thread comes to this point, if someone is blocking, it cannot get in. Okay? So that you guarantee this is properly done without interference of other thread. And also, when this guy is allowed to get in, it's guaranteed this one is already finished. This has to do. So this is one way. Okay. So, but as you see, if this is a very heavy operation, dominate all of your program, then there's no sense if you run this program in multi-threaded mode, because once thread 1 is doing this business, thread 2 is just waiting. Okay? Useless. But in some cases, we do need this mutex lock. And in Geant4, we do have some mutex lock. Okay? For example, initializing each thread, we do have mutex lock. But while we are running events in parallel, we do something else. That is thread local storage. If you put keyword __ thread, okay, it said this object is instantiated in a memory per thread. Okay. So it's safe. This one is thoroughly used by this thread. Okay. And this is another object in a memory. So there will be no interference. Okay. Here, of course, you can use all the computation power of all the threads. But in this case, you have a small overhead in memory because you duplicate a memory object, right? So it's a trade-off. And we try to use this as much as possible, okay? Because we care about the speed, okay? So it's just a toy, let's say, measurement. So this black line is an ideal case. And here's the number of threads, and here's the speed up. So if you have the 2 cores or 2 threads, the performance should be double, 3 times, 4 times, and so on and so forth. This is a black line. And if this part requires 10% of the CPU of the entire program, it goes like this. That if you use the lock mechanism, after 3 threads, basically you don't gain anything. Okay? Even for 10%. If it case of 1%, it's here. While for the case of thread local storage, the performance is much better, but not yet identical, ideal, I'm sorry, because this thread local storage is not exactly an object itself, but it's a kind of address manipulation. So when program comes to this place in assembler, it really check if what is the thread ID. So it's really calculate where should be the address to jump. So there should be a small overhead, but obviously much better than the mutex lock. So it's pros and cons. It has pros and cons of both cases. So please, if you have something have to be cared on the thread safety, think which one you use. And for the case of this underscore thread, Geant4 has a dedicated keyword, G4 thread local. You can use it so that in the future, if we move to a new threading mechanism, you can still keep your program without touching to it. Okay? So instead of just write underscore thread, underscore thread, please use G4 thread local keyword. Okay? If you go to our LXR code browser and just type a keyword G4 thread local, you have tons of it. Okay? So, for example, in this case, let me try to explain what we do for example, the particle definition case. Particle definition, for example, let's say it's pion, pi plus. Okay, Geant4 has G4 pi plus. It has its own mass, charge, lifetime, and decay table. Pion is unstable. And pion also have, as Dennis and Mihal discussed, and each particle definition has its own process manager that registered all the physics processes to be employed. But here, process has to be thread local. We already discussed, because process really calculate each secondaries or something. If this is singleton, it mixes up all the secondaries over the thread. It's useless. So there must be a kind of mechanism to, switch from the shared object toward the thread local object. So what we have here is TL, thread local storage pointer. Okay. So this thread local storage pointer, this is unique for this particular particle type. That is pi plus. And if this pointer is accessed by thread number 1, it says here it is. If it is accessed from thread number 2, it says here it is. So it really changes depending upon from which thread this particular pointer is asked. It's a smart pointer. Okay. Then once, for example, if it is asked by the fourth thread, it comes here. Then here's the TLS point. This goes to this process manager. Okay, this is thread local. It's guaranteed this varies correctly depending upon from which thread this pointer is accessed. So this is the mechanism, okay, that we use. Okay. So anyway, I know it's a bit complicated, and I believe I cannot explain you very nicely. But at least this part, I believe you understand what you have to avoid. Okay. And the problem is, if this happens, it's not easy to detect a problem. Core dump may happen at anywhere because pointer could be screwed up. So crash doesn't happen at this point, but completely some other random place. And even you try the program again without changing anything, it crashes at other place because some other part of memory configuration changes. So once this race condition happens, it's a nightmare. So since you start writing code, you always think about if this method is invoked per thread or global. Okay? If it's per thread, you really have to care if any variable or data member used could be shared over the thread. Okay? So be careful, okay? That's it. Okay, TBB MPI. That's something, for example, TBB is so-called thread block building block library made by Intel. And freely available, yes, but not easy to use. And anyway, for example, CMS is using it in its framework, and Atlas is struggling to use. And I think Alice is using it, if I understand correctly. Anyway, so it's slightly different from what Geant4 offers, but Geant4 does have a couple of examples how to tell how to use Geant4 multi-threaded mechanism in TBB environment. So if you are forced to work for this nightmare, I invite you to look at this example. Okay? So anyway, the thing is that, and also if you run a program in the computer farm, that means there are more than one computer node, and each of them has more cores or threads. In this case, you have to use MPI and message passing interface. Yes. So here's hardware view. So here's network, and here's each node or each computer, if you like, and each computer has more than one core, okay, and shared memory. And MPI gives you this kind of image. So there should be a global master that controls each worker node, and each worker node has more than one thread. And between worker one local master and the thread, we use multi-threading. While communicating from the global master over the node, we use MPI. For example, master broadcast UI command and random number seeds to the workers. Okay? So that the very basic random number seed are managed by the master, okay, through MPI communications. So rank number is basically number 0, 1, 2, 3. Okay? So random number seed, UI command are already, you can deal with it. And Geant4 can take care of it. And histograms, command line scorers, and user-defined G4 run, that are already taken care of by MPI. And sorry, I forgot to update. Now Interpol is also taken care of. One thing we still cannot do is visualization. Over the many cores, there's only one event display, but forget about it. It's not very useful. Okay. And also, this database files, why I don't put it yellow is data distribution is always a nightmare in the supercomputers. Okay. Even if we have just one file, million CPU try to access to this file, it's nightmare. And as Dennis described, there are tens of data files we have. Okay? So that is something we really have to think about. Anyway, we could successfully employ all the 3 million threads of Argonne supercomputer. I don't remember, sorry, exact number, how many nodes we have. But in total, it's 3 million threads. Okay? And nice performance. But I/O is still an issue. Okay? And this is Intel Xeon Phi, although it looks small, but the reality is this size. but still it fits into the bit larger shelf of the desktop. And actually, it's cheap compared to the CPU. The high-end CPU nowadays costs $2,000-3,000, while it's $200. And basically, this single guy is almost equal performance with a high-end CPU. It cannot be computed by itself, but if you have one host CPU, by adding one card or two, you can double or 3 times. So it's a good thing, but quite unfortunately, Intel said it's over. So Intel has already given up developing this. So it's a dead end. It's quite unfortunate. The good part of this one is it runs C++, not CUDA. For the case of GPU, you really have to rewrite the code almost from scratch in a different language of CUDA. But in this case, it really runs in CPU. So it's a really good option, but unfortunately, the price, battle between NVIDIA and Intel, NVIDIA won. So at least in US, all the known next generation supercomputers use GPU rather than this technology. So it's not nice. Anyway, even this night corner is the previous version, and the night landing is the latest version of Xeon Phi. Compared to night corner, night landing, it's 3 times faster. Good. And compared to the best CPU with all the cores, all the threads, still faster. Okay, and price is much less than this core, this CPU. So it's good. And nice scaling. And we have already been supporting the use of night corner for Atlas CMS for several years. And night landing, we supposed to support fully, but given Intel stopped supporting it, we are kind of stopping support, but still you can use it. So anyway, now it comes to the most important part. Reading input file from for primary particles in multi-threaded mode. Okay. So please note, amongst others, primary generator action and primary generator itself is thread local. Otherwise it doesn't make any sense. For each thread, we have to start each event independently. Okay. So you have to pay special attention if you have a reading input file to read. Okay. If you naively write the primary generator action to read a file in multi-threaded mode, what it has is the following. Each thread start to read from the first line of the same file. It means if you have 2 threads, you have duplicate the results twice. It does not make any sense. So you have to write a bit more careful program to avoid this. Okay? Even if you duplicate the same file into 2 and assign to each thread to read different file, it's the same. It always starts from the top. Okay? So here I give you 2 examples. One is, and basically the application depends upon the ratio of the cost of accessing to the data file to the total execution time of each event. If, for example, for the case of high energy physics, one event has a lot of particles with a lot of energy in total. So simulating one event is quite costly. In other words, if suppose you do it in a single core, access to the file, input file, is quite less frequent. Once you read one event, it takes quite some computing time, then you come to that. The other end is low energy example or medical example. each event is quite tiny, with just one particle maybe, with quite a small energy. But you have millions of events. In this case, you often access to the file. Okay? Calculation is small. So there are two use cases. Okay? And anyway, you have to use mutex. Okay? So I give you an example here. The first is high energy case. And let's take a case that we have HEP-EVT interface or HEP-MC interface. So we access to a file that has event. Okay? Here, we intentionally have static keyword. So interface that reads to a file is singleton. Okay? This guarantees once this guy reads first event, next time it reads the file, it goes to the second event, regardless of which thread it access to it. Okay? And if you like, the example extended round event RE05 takes care of this kind of case. Okay? So here, constructor, please note constructor is invoked per thread. So we do have a mutex lock here. And if HEP-EVT interface is not yet instantiated with file name. Okay? Given this new operation returns a valid pointer here, and next time other thread come to here, it already have valid pointer. So this object will never duplicate it. Okay? Again, here, to delete it, you delete only once. And here, you have mutex lock. So when thread A comes here, it reads a file. When thread B comes here, it waits if other thread is reading this file. And when get is open, it comes in and use exactly the same object to read a file, so that it's guaranteed now it reads the second event. Okay? So in this case, mutex lock is that it. Okay? Any question here? For high energy physics case, this is enough. Any question? If not, for lower energy case, we do the same, basically. Okay? But if we naively do it, there will be a problem. I will explain. And also, please note, the file reader and particle gun are different objects. In the previous case, physics generator itself is a singleton. Here, only the file reader is a singleton. That file reader that takes care of reading file is shared. Okay? But particle gun is not. So file reader is static. And the constructor, we have mutex locks here. So we create only one file reader. We can unlock at here if you like. And actually, this lock mechanism, if there is no unlock is implemented, if program comes to the end of the scope, it is unlocked automatically. And delete a file, delete a reader at the end, yes. Then, here's primary generator. Generate primaries. Okay, so it read a file with a lock. Okay, and once you get the 3 momentum, exit the lock, and set the value to the particle gun. Okay, it's okay. So up to here, basically it's the same as previous recipe. But in addition, this file reader has some trick. some file reader class. It has a buffer of the event. The idea is, if you don't have a buffer, this mutex lock will dominate. So performance will be broken. Because in this case, processing time of each event is short, while you still have to access to the file very often, and access to the file is costly. So if you naively do it, this mutex lock will destroy the performance. So what I did here is access only once per 100 event and read file into the memory. Then every time get an event here comes, basically just pop up from the memory. Okay? And only once in 100 event you access to the file. Depending upon the memory size or whatever, this could be 1,000 or million. The idea or key thing here is the reason why I split it particle gun and the reader is this file reader reads 100 events at a time and it keeps it. And this 100 event will be dispatched to each thread, okay? And set to the particle gun. With this way, you can really avoid the heavy overhead of this mutex lock. Got it? Because for 99% of the case, of course, it's still mutex locked, but it just goes through here and just pop up from the vector and unlocked. It's quick. Okay? The key thing is accessing the file on the disk is a heavy operation. Okay? For the case of low energy application, processing time of each event is small. If you have direct access to the disk every event, it's end of the story. Okay? And please note that mutex has a performance penalty anyway. So please be careful and use it only when you really need. Okay? If you put mutex everywhere, it's single thread mode. Okay, that's it. Question. And I know. Someone said we are giving you too many information in 1 week. Yes, go ahead. Yeah, actually, regardless of master or master is also in a thread. So it's the same thing. That's key. Anyway, all the threads share the memory. So you anyway have to have one file reader shared. That's it. Yes. Yeah, so I know we are giving you too much of those information. So just remember, there's something I discussed about threading in this slide, and when you really need it, come back, because all the presentation we have will be kept for at least a year or two. Okay? So all you need to remember is we discuss a lot of different things. That's it. You don't need to remember any detail. Okay, let's get into the break.